Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. I was going to let the song finish, but then there was like another 2 minutes left in the song, so I figured let's just go ahead and get started today since it's going to be a bit of a shorter stream. Only about an hour and 30 minutes today as opposed to my 2 hours yesterday and 4 hours the day before that. So we'll just see where we go. The first part of the stream, like I have been doing for the past few streams, is to go through these old Algorithm Archive PRs and see what we can do with them. I just want to get some forward movement made in these PRs, and then we can go from there. So let's take a look at this Monte Carlo Scratch implementation, because I think it's actually ready to go. I realize like we're doing a lot of this Scratch stuff recently. Let's see. So let me just go ahead and pull this guy and see what it looks like. And then hopefully this one's also ready to go. I realized yesterday we did a Scratch PR, and it's kind of weird that we're doing another Scratch PR today, but it is what it is. CD Projects Algorithm Archive. I just went through the PRs. I saw one with a language that I knew how to edit, and we'll go with that. So let's go ahead and grab this branch. Yep. Okay. We'll be doing Julia in just a minute. So first I'm going to review some Scratch code, and then we'll move on to Julia. So it's going to be, today what we're going to do is we're going to do a bit of Scratch code, and then after that we're going to do a bit of Julia code where we write the iterative function system, and then we'll go from there. Honestly, that's probably all we're going to be able to get done today. We might move on to C++ from then. I'm actually genuinely surprised at how Julia, specific you are, Freeman. Like, the moment I say that, I'll be doing another language, you're out. You don't even try to stay. But that's okay. I mean, I'm not saying there's anything wrong with that. I'm just saying that I've never met someone on stream that was so focused on Julia, and there's something to be said about that. This particular stream is pretty much language agnostic. As long as you're not using MATLAB, it's fine. We do put we have a little caveat in there for MATLAB because, oh boy, there are so many things wrong with that language, and I'm not going to get started on it because every time I get started on it, I end up having a 30-minute discussion about how much I hate that language. So let's go here, localhost, and what am I actually reviewing? Monte Carlo Scratch. So let's go down to Monte Carlo, and let's take a look at what we have. So let's move it to Scratch. Scratch here. Looks good. Oh, there is a bit of white space under there, isn't it? Closure. Let's go to Scratch. It looks... Yeah, let's just crop these images. Why not? Seems fine to me. So we're going to CD into projects, Algorithm Archive. LS here. Oh, can we crop the images? They're SVGs. Right. Other than that, it's fine. It's just there's a whole bunch of white space under this guy. So what do we need to do there? Can we push to this PR? I would guess so. Let me think. So the issue with this is that these guys are generated. These guys are generated via some Scratch blocks code. So let's find that Scratch blocks code, regenerate the images, and then have the cropped ones. Change the header as XY length. Oh, well, if we can just do that. So let's CD into projects. I'm already there. Project Algorithm Archive contents. Monte Carlo integration. LS here. Let's CD into resources. LS. Nope. CD into code. LS CD into Scratch. LS. And we have these guys. And then also Monte Carlo.txt. But we should have... it must be this one. Yeah, that must be it. So let's take a look at the Scratch VD then. VI algorithm.svg. So you said it's width and height, right? That's what we're looking for. So let's see what the width and height are that we actually need here. Let's go to GIMP algorithm.svg. And we'll just see what the width and height are supposed to be, and then we'll go from there. Okay. Oh. Well, that looks right to me. Okay. Now let's go into incircle.svg. And again, this is probably going to look... Yeah, that looks right to me as well. Okay, let's open it up in Mirage algorithm.svg. Yep, no white space there. So let's go into VI vi Monte Carlo algorithm.svg. Why is there so much white space under this guy? Let me change the language. See? C goes down there. Factor goes down there. Clojure. I'm not exactly understanding why there's so much white space under that image. I don't know if inspecting won't give me anything, but if it'll give you something, let's go there. Inspect. Yeah, I honestly don't even... No, so this image... Let me open up this image. View image. X here. Can I... How do I... Let's save the image. Let's see. Well, let me just wget this image. CD pictures. Wget this guy. And let's take a look at Mirage. Algorithm.svg. Yeah, again, it looks fine. I figured as much. I just thought maybe. Because what's actually happening here... I mean, if I just drag the image out, you can see that there's a lot of white space at the bottom of that image. So... Right. Why would it encode? Inspect element. Image class. If we just output them as PNGs, this would solve the issue. Let's see. Maybe it's just maybe it's just this browser. What happens if I open this up in Chromium? Will this work? Change this to Scratch. No, still a lot of white space. So here's, yeah, the whole image is huge here. It's 872 by 1090. Let's just open it up and fix that then. CD into code, Scratch, and then let's go into vi algorithm.svg. And let's just change the 1090 to... Let's change this to 800. What the... What? What? Okay. Never seen that error before. Let's change this to 800 and see what that does. Write this, and we will just recompile Gitbook and see what it does. There's probably some strange SVG shenanigans. Yeah, that's probably right. So what we just did is we made the height less than the width, which doesn't make any sense here. But let's see what happens. So we're going to refresh the page. And let's see, we're on... Width is 872. Yeah, see, now we're just cutting off the image, but we still leave that white space at the bottom. Okay, let me try changing this back to 1090. So git checkout algorithm.svg, and we'll just do convert algorithm.svg into algorithm.png. Okay, so now we have algorithm.png, and I'm just going to go back into the directory. Let's go into vi Monte Carlo integration algorithm. Let's change this to algorithm.png. SVGs have strange sizing issues in browsers. Maybe ViewBox will do the trick. What is a ViewBox? Yeah, maybe I should figure that out. So, as a PNG, does this work? The answer is yes. It does work as a PNG. So, I'll look up the SVG ViewBox and see what we got. Attribute ViewBox. Take a look. Thanks for that, by the way. Okay, so it looks like we'll probably start doing some Julia coding at around 8 o'clock p.m. Today we're going to be coding up iterated function systems in Julia, and we'll go from there. Julio and also Hums, thanks so much for following. Really appreciate it. Okay, so SVG ViewBox is going to be 0, 0. How do I... Let's see. Essentially a different way to specify size. So what you're saying is... In user space of an SVG viewport, the value of viewbox attribute is a list of 4 numbers, min x, max. Okay, so what if we just do SVG viewbox? Let's just see what happens if we put this in here. So I'm going to, I guess, open this up, paste it in here, because this is clearly, so with relative units such as percentage, okay. So something like this. What happens if we run this? Does this actually compile? Let's see. So this should create a weird image on top of the image that we already had. So we'll see what happens if we look at the algorithm archive now. So here it is. Yep, so we have our little box there. Okay, so now what I want to do is, I guess I want to put in code scratch algorithm.svg here. Let's see, rectangle. No, we don't need this anymore. So is this all I'm looking for? I don't know. Let me see. I have no idea how to do any HTML. Like when I was younger, you know, like, and you start learning to program, obviously one of the first things you want to do is make a website. I've did a bunch of little things. No. Okay. Let's take a look. How do we put an image in there? Marker pattern, SVG, number, symbol, view. Width and heights in SVG has strange behavior. We also resize the image in CSS. Right. So what I'm asking is, how do we put an image into this view box? So here we have view box, rectangle, height. Let's see. So using as a main SVG element. I don't know what you mean. I'm so sorry. Oh, you want to put this in SVG, in the file itself. Instead, it'd be essentially the same as the usual width and height attributes. Yeah, I still don't know if I know exactly what you mean. I'm so sorry about that. So we have this SVG view box in here. I don't know what XML and S stands for, so I guess I can just get rid of that. Because that's how this works. Using SVG viewbox with image. Let's see what we got. How to scale SVG. Okay. SVG is not just an image. Original size. Right. Let's see. iframe. I was hoping for just literally the code. But this is not what I'm looking for. Yeah, all I need is the code. Yep. Okay. Nope. Viewport and viewbox. Image X. Width. Let's see. Image elements. Yeah, I know it's supported. Yeah, but the problem is we have that. So we have image class here. So X equals 0, Y, width. So we have the same thing. Width is equal to something like that. I mean, maybe I need to define the height. Let me see what happens if I define the height. So we'll do. In fact, let's just not have the height argument. Let's see what happens there. Because the height is already specified in the SVG file. I feel pretty proud of myself today. I took some Microsoft machine learning demo code and spit it out by 100 times. How did you do that? We could edit the SVG file, but the SVG file is put out directly from. Oh, I think I'm still using a PNG file. Yep. So because the SVG file width was already decided in the file, I think if we just don't have a width, no, that gave us a white space at the bottom. They coded 4 deep nested loops. Fair enough. Okay, so we have this. Just comment that it looks weird and have the pull requester figure it out. That's what I did, but they haven't figured it out yet. So I think Yeah, I don't know what to do here, because I don't think they can figure it out is the problem. Um, but I guess you're right. Maybe what I'll say is that we can. There's some CSS SVG shenanigans. Yep. Essentially, the SVG image has a size, but resizing it in CSS is more like resizing the viewport than the actual image. Right, but here's the thing. We're not resizing it in CSS so far as I'm aware. Not with this, anyway. Again, we could output them to PNG. So maybe that's just what I comment. Maybe that's where we leave it, and we don't really talk about it too much more. So this PR is ready to go, except that the SVG image is too large, has white space. Has white space under it when rendering the algorithm archive. Let's see. I can try to take a look at it. If you cannot figure this out, there are some issues with CSS and SVG. We can relatively easily convert everything to PNG. Wow. Where and it will work fine. However, there might be a way to get this to work with a view box. Let's go ahead and give them a link. Yes, I tried it on Chrome and Firefox on Linux. Here. There, and here. Okay, so this PR is ready to go, except that the SVG image has white space. I guess I'm going to lowercase this. SVG. I'm going to lowercase this as well. CSS. Okay. Well, I don't think the browser really matters too much, but we'll say this was tested in Firefox and Chrome. On Linux. Okay, cool. Okay, that's fine. So that PR wasn't merged, which means we have a bit of a question. Should we go ahead and move on to the next bit where we work more with iterated function systems and stuff like that? Or should we try to find another PR that we can merge today? I don't know if we can, because I think a lot of them, like all of these PRs that are available, require a lot of work. I mean, otherwise they wouldn't still be available. I would have merged them before. So it's either an issue where the PR maintainer or the person who suggested the PR didn't come back and fix something that was clearly still an error, or we just didn't get to it fast enough to review because we didn't have language. We didn't have specific language knowledge in the case. Like, for example, I don't know Go, x86, Kotlin. All the languages I know have been adequately reviewed, except for this one, which is just, this PR can't be merged because it's incorrect. That's one that we can't merge. Vim language was ready to go, but the maintainer hasn't come back. But that's okay. It's kind of my fault for getting to this so late. So it is what it is. Unified Lua code style across multiple pages. Then we had Vexitose. I think we are okay with actually getting this one in. Because honestly, I know a bit of Lua, and literally all he did was add some comments, and I think this is relatively good to go. Let me just go ahead and let's do this one today. I think this one can be merged. So let's go ahead and check out this guy really quick. So we're gonna do quit exclamation mark, git checkout master, git stash, why not, git checkout master. Now we'll grab this PR and see what we can do. So So basically what it is proper use of local, proper use of snake case, remove a bunch of dead spaces, fix Monte Carlo to be equivalent to other implementations, add to comment and Julia implementation to Monte Carlo code. Okay, let's go ahead and take a look at this, and I think this should be mergeable, and then we'll move on to the fractals and stuff like that. And again, guys, sorry for the short stream today. I have basically another hour left in stream. The reason for that is just I quite frankly had meetings that lasted a bit longer. Every Monday I have a meeting that starts at 5 o'clock p.m. and I start streaming at 6 o'clock p.m. So that means that the meeting will be relatively short. So let's check the files touch just to make sure that they all work. So he touched BOGO sort, bubble sort, Euclidean, Huffman, and Monte Carlo, and Thomas. Okay, he touched a lot of them, so let's just go one by one. So we'll start with BOGO sort and bubble sort. So BOGO sort, and we'll change this to Lua. Where's Lua? Lua. What? Where's Lua? JMP. What? Lua. There we are. Yep. Good to go. Bubble sort. Yep. Seems good to me. Okay, so the next one's going to be Euclidean and Huffman. Euclidean, again, looks good to me. And Huffman encoding. Where's Huffman encoding? Should be here. Oh man, that's some code. Okay, so the next one's gonna be Monte Carlo and Thomas. So we'll go to Monte Carlo. Well, Thomas first since it's right there. There should just be some code at the bottom here, so that all fits. And then finally the Thomas algorithm, which should be, so we have the Euclidean algorithm. I'm looking for matrix methods, and it should be, no, Monte Carlo is right here. Okay, looks good. Great. I'm happy with this. Approve. These changes should have been merged in months ago, but I was afraid to review it because I don't know Lua as well. These are all positive changes. Okay, let's go ahead and prove that guy. And I'm happy enough with that. And then we'll move on to the fractals and stuff. So squash and merge. Confirm squash and merge. Good. Okay, that's another PR merged. I know this whole like merge one PR a day, depending on who you're talking to, could sound kind of ridiculous. But the thing is, we have a lot of PRs open. And I'm just hoping to get some forward momentum there. I know we'll get a lot of forward momentum when I put another video out, which is why, again, I'm working so hard to get this upcoming video out. But we'll see how it goes. So we're going to CD project algorithm archive really quick, git branch, and then we'll do git branch, git branch -d, and we'll do Vexitose Lua fix up just to remove this branch. I think I need to check out master. There we go. Okay, so that's good to go for now. And let's move on to the next bit of today's stream. So we are going to git checkout IFS. Yep. CD into contents IFS. Okay. Oops, sorry. L is here. And let's go ahead and run the algorithm archive one more time. So git book serve. There we go. And I'll show you where we're at with the current chapter for the iterative function systems and where we're going to go. So for those of you who may not have been here before, let's CD into projects, algorithm archive. Actually, CD into projects, Simuleos, L is here, and we're going to CD into fractal. Let's go ahead and run G++. Hey, that's me. Wait, what's you? I'm sorry about that. So run G++, and then we're going to create a video really quick, and I'll show you what we're working with here. I've never been here. Wait, what do you mean you've never been here? Hi, how are you? Yeah, if you guys have any questions, comments, concerns, anything like that, just let me know, and I'll totally address it as soon as I see it in chat. Yeah, welcome to the stream. It says Funny Flywheel and also myself. So we've got another hour left in stream. I'll talk to you about what the project is that we're working on in just a second. We're just about to switch topics, so I'm happy to see you here. Ali Hashmi, thank you so much for following. Really appreciate it. So yeah, we work on a project. I guess while this is rendering, we work on a project known as the Arcane Algorithm Archive. Let's go to, I have my local host here. You're the boss man. Hey, thanks. I appreciate that. Yeah, guys, if there's a notification, just let me know if I miss it. I'm doing my best to keep up with everything, but I'm doing a very bad job recently. So like, if there's like something weird that pops up that I wouldn't, normally see, just let me know. Let's see. Freeman7 commented on adding PID control chapter. Oh, right. Thanks for that. I really appreciate it. And let's see. I have one last thing I have to check at. Okay, good. Why am I getting so many notifications in the middle of the stream? I almost never get any notifications during this time. Okay, so we're working on a project known as the Arcane Algorithm Archive. This is, your one-stop shop for algorithms. The idea is that we teach you the algorithm in full. So here's all the details you need to know about what Gaussian elimination is, why it is this way, all of that kind of stuff. And we also provide these code blocks in whatever language you think you learn best. So Julia, Java, Rust, whatever, it's all here, right? So the idea is, for those people who want to learn algorithms and maybe aren't the best at pseudocode, although we will try to provide pseudocode implementations in a bit, I think this is a very good way to learn these algorithms that we have. We give intuitive explanations, and we do everything we can to provide a deep, intuitive understanding of the algorithm, and that's what we try to sell. In addition to this, we also have my YouTube channel, which is LeosOS. So youtube.com, LeosOS here, where we also put up videos and stuff like that. So between, Twitch here, where we talk about algorithms all the time, the Algorithm Archive, where we put, in-depth discussions, and YouTube, where we it's more or less advertisements for the rest of the ecosystem. We've got a good system working on here. I think all three of them kind of blend well together. It's just I'm massively behind. My last YouTube video was like a year ago, so I'm really far behind on YouTube videos, which is why I'm really focusing on getting some content out now. I'm also behind on Algorithm Archive work, but that's slightly beside the point. Ignite OP and T Jesterbrook, thanks so much for following. That's really cool. I love algorithms, even though I don't know much. The goal of the Algorithm Archive is to be somehow a way for people to get into algorithms who are not used to, I would argue, the rigorous mathematics beneath it. We don't require a huge amount of mathematics, although admittedly I'm on Gaussian eliminations, which is very mathy. But it's not like what's required for like CLRS or something like that. There's a different level of mathematics needed here. Okay, so what are we working on today? Well, today we're working on a particular visualization, and here's where I need your help. I'm going to ask you guys a question. So let's go ahead and run mpv temp video.mp4 loop 0. So yesterday we made this animation. This isn't the best animation. This wasn't the one I thought I was making. Right. So let's do a slightly different animation. So we're going to do mpv vi projects. I'm actually in the right directory. Vi Sierpinski .cpp G down here, and let's just run. We'll do Sierpinski Hutchinson, and we'll show you the visualization. So let's run G++, and then /Sierpinski, and then we'll go from there. Any chance we'll make a video article on special methods for PDEs? I really want to. I really, really want to. Now, we've got some pseudo-spectral method already in there, although admittedly, I think I kind of... The thing is, so we have the split operator method. The split operator method is obviously more varied than just for quantum systems. However, I genuinely feel that So, okay, what is the split operator method? You might be asking. So the split operator method is a rather simple method. You take a wave function, you multiply by some operator in position space, you take the FFT of it, multiply it by some operator in momentum space, and then multiply it by position space again. That's all you do. You flip back and forth between position space and momentum space. Now the thing is, a lot of times when people talk about this method, they talk specifically about solving the nonlinear Schrodinger equation, which is this equation up here. Now, I specifically put in the Gross-Pedievsky equation. Now, the truth is, it doesn't have to be the Gross-Pedievsky equation. Any nonlinear Schrodinger equation will do. Right, there's nothing in quantum information yet. I intended to put stuff in there, but I haven't put anything in there yet. So, there's a lot of information here that I think is best understood when you think about quantum systems, because it's the other place that the split operator method is used is usually in like fiber optic simulations, and quite frankly, it's difficult to understand that perspective, in my opinion, because it doesn't have this idea of momentum space in the same way. So that's why I put it under quantum systems, because it's used very regularly in this space. But we might want to put it in a different space later. As far as quantum information is concerned, look, we did so much for quantum information. Oh boy, we did so much for quantum information. We wrote Grover's algorithm, Shor's algorithm. We did so much stuff, but I have not yet been able to put it into the algorithm archive. So let me just really quickly, I'm going to make this huge, and let me just do cd backer directory and then ls in this directory. So we've got a huge number of we did affinity propagation, Barnes Hut. Let's see, Computus, domain coloring, backwards Euler method, finite difference time domain, spectral methods, fractals, which we're doing now, genetic algorithms, Gale-Shapley. We did gift wrapping. We did so many things here that were never put into the algorithm archive. And so what I'm doing here is I'm slowly but surely getting through the backlog of things that we've done here on Twitch, maybe even a year ago or 2 years ago, and slowly turning them into videos and turning them into algorithm archive content. So as far as the quantum information is concerned, there's a lot of quantum information to be done. We even invented our own library to evaluate quantum circuits, and it turned out really nice. But we didn't yet write it up. So that's where we're at with a lot of stuff in here. So that's unfortunately the case with the algorithm archive. There are some chapters that are ready to be written, they just haven't been written yet. Spectral methods are useful for heat over time and space. Right. Spectral methods are some of my favorite methods. So for those of you guys who don't know, gift wrapping does have a chapter, but it's a stupid chapter, and I don't like it. So here's our gift wrapping chapter. Jarvis March, I have nothing. I have nothing here. If you look at the Jarvis March video on YouTube, it's so good. Like, I mean, it's not good, but I like it. I like it a lot. Of course I like it a lot because I made all the videos, but let's see, where is it? It's, I guess, videos. Where's my gift wrapping video, man? Here it is. Oh boy, man, I missed this so much. Like, look at these, the animations were great. Also, my ears are big, but you know. So we made a bunch of animations of like gram scan. You know, here we have gram scan happening. These animations are nowhere in the algorithm archive. So that's why I don't see the chapters as complete. We don't have gram scan really in there. We don't have Jarvis March really in there. And we definitely don't have Chan's algorithm, right? So it's like, I don't know. It's something that I want to put in there, but it's not there yet. So that's where we're at. I don't know. So there's a lot of stuff in here that I need to update the algorithm archive with, but I don't have time for. I don't know who I said thanks for following to, but T. Jesterbrook and Skirios Ka, thank you so much for following. Really appreciate it. Okay, so let's talk about what we're doing today. So we're going to do the last MPV. Okay, so here's what we got. Wait, subtitles hidden? I didn't know I could do that. Okay, that's something. Okay, so here's what we got. We have an initial triangle, A, B, and C, or something like that. They generate 3 children, little a, little b, and little c. Now these 3 children generate 3 more kids, and the 3 kids go separate ways. You know, one group of children wants to move halfway towards the top point. Another group of children want to move halfway towards this point, and another group want to move halfway towards this point, right? Now all 3 of these, or all 9 of these children then generate more children again, and they kind of follow a similar trend. A third of them want to move up north, a third of them down to the lower right, and a third of them to the lower left. So we get another group of children like this. And those generate then another group of children, and then another group of children, and another, until eventually you start to see the Sierpinski triangle start to form. Now, this animation is what we're working with, and this is kind of what we're talking about today with the heart of iterated function systems. Would you be interested in content about direct global optimization algorithm? I don't know the direct global optimization algorithm, actually. It depends on how specific it is. The truth is, that's obviously not gonna, the truth is we're still kind of fuzzy on whether we allow contributions from other people, right? The answer is we should. We definitely should. But it's just, I don't know, we definitely should. It's just that these reviews end up being very rigorous because I end up being very sticky about the text more so than the code. And I feel like we don't really have any good chapters until the Computist chapter. I feel like we don't have any really good chapters to be like, hey, make sure that you have all of this in your chapter before it can be merged in, right? We don't have like a guideline, you know? And it gets really sticky because some people will say something in their text, and I'll be like, hey, could you just rephrase this to be this or something like that, right? I have to play the role of an editor. And some people get miffed about what I say. I'm like, hey, could you do this? And then they're like, nah. And I'm like, well, I would argue that this is more correct than that, and this, and it just ends up being a bickering contest, and I don't really like that. Direct global optimization algorithm. Let me just do this in Google really quick. And let's see. A direct global optimization algorithm. I was looking for cited by 270. I mean, it's probably good enough. Anyway, there's a huge chapter on optimization that we can do. You know, like there's obviously just starting with Nelder-Mead, and then going into all the different optimization strategies like gradient descent and stuff like this. It's a huge subset. I mean, like, there's so many optimization algorithms out there. The truth is, we accept anything in the algorithm archive. There's so many algorithms to do. But I do rigorous, like, the chapters are very hard for us to merge in right now. So I don't know how to answer that question. Okay, so let's talk a bit more about these iterative function systems. I'm going to make this small. Or default rather, and I'm going to open up Zernal-PP. Okay, so here's my question to you guys, and this is one good thing that I'm happy we have people here, and they can give me their opinions on this, okay? Then I will not attempt it. Not for now, like maybe in a few months, and I'm so sorry about that, but I do really appreciate it. Like, I really do appreciate the support. It's just I'm not... You can clearly see when you're reading through the algorithm archive that it's in its beginning stages, and it's been in its beginning stages for years. And this is in part just because I don't have the time I need to actually work on it. And I've mentioned this so many times before. It's kind of like my dream job to be able to work on the algorithm archive and YouTube and Twitch as like my full-time job. Like, this is why I spend a few hours on it every day, and I do everything I can to make it successful. I mean, just yesterday, right? Like, after stream, I was so tuckered out. I was just ridiculously tired. And I spent the whole day, the whole rest of the afternoon, just looking up algorithms in order to fit the theme for this project I have in mind called Algorithm Advent. Algorithm Advent. I don't know why that was a capital D, right? So my goal, and this is definitely not going to happen, but I've been wanting to do it for years. My goal is to be able to put out a single video. Every single day in the month of December. From basically, starting November 29th, because that's when Advent starts, all the way to December 24th, where we just put a new algorithm out. Like, the algorithms will already be in the archive, but we put a new video out for it every day. I recently learned of self-organizing features, maps, which is one of the simplest dimension reduction techniques I've ever seen. Oh, interesting, actually. We do a lot of dimension reduction. That's probably something I should look into. Is this like AOC? What is AOC? I'm so sorry. Advent of Code, right? It'd be something like Advent of Code in a way. Yeah, something like that. But it's not. It doesn't have to be actionable, is what I'm saying. Like, people can just watch the videos and enjoy it. They don't have to they don't have to go to the algorithm archive and implement it in their own language and all that kind of stuff if they don't want to. But I really want to give them the option. So what I'm trying to do this year is I am really trying to ramp up production, put out as many videos as I can, get really good content out, and really bring people on to Twitch and YouTube and things like that. I mean, I've got 65,000 subscribers or something like that on YouTube. If I can hit 100,000 subscribers, like, that says to me that it might be about time to think of this potentially as a career. So that's kind of what I'm working towards this year, but we'll see. Sublake, thanks so much for following. Really appreciate it. Okay. We're not going to talk anymore about Algorithm Advent. Let's talk about the chapter and do some Julia coding. Okay. Yeah, sorry, the YouTube isn't... my bot's down, so let's just go YouTube here. So for those who want links, here's YouTube, and here is the algorithm archive. Okay, so first the question. Let's go back really quick to here. The way I have iterative function systems written, first of all, it's a subset of the plotting chapter, which I may not want to do. Let's talk about what we're doing here. So we have a point A, B, and C, right? So here's A, B, and C. And we have three functions. Function 1, function 2, and function 3, okay? So here we have P plus A over 2, P plus B over 2, and P plus C over 2, right? So the idea here is that, you know, we have a bunch of children, and these children follow one of these three paths. So A will generate 3 kids, you know, one will move halfway towards B, another halfway towards C. C generates 3 kids, one moves here, the other here, and B generates 3 kids, right? Then these guys generate 3 kids, so you get 3 points here, 3 points here, and 3 points here, right? And then you can slowly start to see your Sierpinski triangle start to form. Now, I think that this is one of the most intuitive ways to describe an iterated function system, right? We're literally just iterating through the functions and taking all possible paths at any given point in time, right? However, the most common way that people talk about iterative function systems is through something known as a chaos game. And here the idea is slightly different. You still have your A, B, and C, but this time you put in a random dot. Well, actually, let me show you the chaos game up here. This time you put in a random dot. Let's put it over here, right? And then it just randomly chooses between one of these three functions. It might move, I don't know, halfway towards A, and then it moves halfway towards B, and then, I don't know, halfway towards C or something like that. And at some point, like maybe right here, it lands very, very, very close to the Sierpinski triangle. From then, no matter which function it chooses, it will always be on the triangle, right? So then if you do 1,000 iterations, 10,000 iterations, and you just keep having this dot move around and around and around, it will form what is the Sierpinski triangle. So that is the most common way people have to implement iterative function systems, but I think it's not very intuitive, right? So the way I looked into this is the way I describe this chapter is I start by talking about the Sierpinski triangle. Then I talk about what happens if you put a square in there, and I say, okay, well, this is a bit weird, and I'll show you the square animation in just a second. And so then I talk a bit about chaos games and attractors, because even though this I don't think is a good way to understand the iterative function system, I think it is a good way to understand what's known as an attractor. Right? Because the idea here is at this point, when following this iterative function system, slowly but surely ends up getting closer and closer to the Sierpinski triangle, right? So it's attracted to that shape. And so I think, yeah, on the one hand, it's not very good to describe the function system, but on the other hand, it's very good to describe that attractive mechanism, right? So that's kind of how I have this split. So my question is, for the code itself, should we? I think, for the code itself, we should only implement the chaos game and not implement the iterative function system. The reason for that is, in its full, and the reason for that is the chaos game is, first of all, the most common implementation of iterative function systems. No one ever does this thing where they follow all of the children, because if you follow all the children, it quickly becomes exponential, right? You have A generating 3 kids, it generates 3 kids, it generates 3 kids, you know, you just have a bunch of children, like a huge number of children, right? And this is not a good way to track anything computationally, right? Because it just exponentially blows up. You know, here's your Christmas tree. So I think I'm personally of the opinion that we should really only implement this chaos game. Mandelbrot Disciple, hey Lux, how are you? I know chaos and fractals for years, but what it looks like a game, which use is that? What looks like a game, which uses that? Is F1 of F2 equal to F2 of F1? F1 will bring you halfway here, and then that will bring you halfway here, whereas the other one will bring you... No, Freeman, that's not true. F1 of F2 is not equal to F2 of F1, and that can be simply seen on a line. So if we have a point here and a point here, F1 or F2, yeah, F1 will bring you here, whereas F2, okay, so let's say this is point 1 and this is point 2. So F2 will bring you here, and F1 will bring you here, right? And then the next path would be the next path would be either here or here, right? So like it doesn't bring you to the same location. No, I don't know if I did a good job of describing that, but yeah. Hey, classical uncle, nice emote you got there. Okay, so let's start with the chaos game, and we'll go from there. And again, for those of you who may have just come in, you may be not following so much, the chaos game is simply a way for us to visualize this attractor. So let's show you what we have for that. We're going to CD into projects, Simuleos, Fractal, LS here. So typically the visualizations look something like this. So those are an MPV, video .mp4. So they typically look something like this, right? You have so many points that are being generated at once that you just see the triangle appear out of nowhere, which is why it's not very intuitive for iterative function systems. But again, let me show you what we've got elsewhere. So we're going to do vi Sierpinski.cpp, move down here, and let's just run the Sierpinski chaos. So let's go ahead and do /, let's do G++. And then we'll run /Sierpinski. Okay, so, but one way you can understand the chaos game a bit more is by drawing the triangle in the background, and then after that, drawing the first 20 iterations of the triangle. Let's see, Philip V18, thanks so much for following, really appreciate it. I thought I was smart until I followed this channel. You're smart, man. Don't ever think that you're not smart. Just because you can't follow this channel, I mean, realize that, I mean, I've got a PhD, right? Like, I've spent years learning arcane things that no one will ever care to learn. So, don't think you're dumb. And the people in this chat are amazing, you know? Like, they're incredibly intelligent. So, you know, you've just come to a little bubble of people who learn for fun. And hopefully you'll join the bubble. Together we'll be bubble bros? Bubble, I don't know if that makes sense. But together we'll, we'll learn more. Street Maniac, can I ask how old you are? I am 28. No, 27. Crap, how old am I? 27. I'll be 28 next month. Bubble Buddies. That's what I should have said, Bubble Buddies. I follow like 10% of it, but I like it. That's cool, I'm glad you're here. 10% still a lot, you know. So, I feel like sometimes I'm kind of demeaning to myself and people in chat. I don't mean to be that way. Like what I just said could have been interpreted to be a bit demeaning, and I didn't mean it that way. I meant it just to be that, you know, first time you come into this channel, probably you don't understand what's happening, and then you figure it out. You know, slowly but surely it becomes more understandable. Okay, so for this visualization, we're going to draw the Sierpinski triangle first in the same way we saw before. And then once the triangle's drawn, we're then going to draw the first 20 iterations. So our point starts here, then it moves down here, and then over here, and then over here, and then over here, and over there, and then up here. And at this point, it's kind of on the triangle, right? So now any future points that it generates will be on the Sierpinski triangle. After this point, you know, it moves, let's see, where does it go? Down here, again, kind of on the triangle, 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 triangle. All the other ones are on the triangle, right? So that's what I'm saying over here. Eventually, your point meanders its way onto the triangle, and then will always be there. Greater Toaster, thanks for following, really appreciate it. J Maru, thanks again for following, really appreciate it. I'm reading through an IBM 370 and Z architecture manual right now, and it's not something anyone should inflict on themselves. I had to read a hardware architecture manual for class. My hands are still unclean. Yeah, I don't know what to say. So I'm gonna let that play while we start writing code to do the chaos game in Julia. And that will be probably the remainder of today's stream. I know it's going to be a short stream. I know I started late today, but hey, I'm happy you're here anyway, and we'll do a longer stream tomorrow. MPV temp video.mp4 loop 0. We'll just let this play in the upper left-hand corner, and let's get that Julia code written. Sorry, Freeman, it took so long. Okay. So CD into code, and I'm also going to do the same thing over here. CD content, what am I looking for? Iterated function system, code, Julia. And we're going to CD into Julia. So the truth is, I did just start writing a bit of Julia code before stream. And then I thought, this is probably something perfect to do on stream. So I stopped myself from doing it. Let's see. So let's see, what do we have here? So are you just drawing every point forever, and then eventually you're going to draw the triangle? You're just drawing one point, and that one point just goes through all possible functions, and it just keeps moving again and again at random. So you just keep drawing until eventually you draw a triangle. So it's not forever, but it's like to 20,000 or something like that. Let's see. School project, plus I'm pretty interested in optimization and embedding systems. That's really interesting. Okay, so one thing to note. Let's go into vi ifs.jl. Do I already have this written? Oh, I bet you I do. cd, let's just make this huge. Why wouldn't I have it written? How would I not have it written? I've done the iterative function system so many times. Surely, projects simuleos, fractal, vi-ifs.jl. Oh. Oh, man, let me run this one. Julia, ifs, does it run? Load error, images. Julia, oh boy, this is going to be exciting if this runs. Add images. Let's go ahead and include. Let me read the file again. So I'm not going to tell you what this is. Foldster knows, but I'm not going to tell you what this is. This could be really cool, or it could be a complete dud. Let's go to vi-ifs.jl. Go down here. I'm running with, that seems like a fair number of points. So now let's run include fractal, ifs.jl. I don't even remember what I ran last with, but let's let it go. Let's see. I love the modeling verification steps of embedded control design. I hate implementing it. Yeah, code is done. Stream is over. See you later, boys. Wait. What do you mean your code is done? Oh no, my code's not done. This is something I wrote a while ago. So this was an extension to iterative function systems that was used to generate some really, really cool looking fractals. Foldster generates a huge number of these fractals all the time. It's just really cool. So I wanted to I wanted to see if this still works. I don't think it will, because I wrote it like on Julia 0.6 or something, but hopefully the API is stable enough that it still runs. But we'll see. Let me get some water. Also, I don't remember how long it took to precompile. That's my one big problem with Julia. It just takes forever to precompile. And I know compilation times in C++ are probably longer in some cases, but yeah, it takes a while. How about we let this run in the background while we start writing the other code? Hey, Neopiece, how are you? I feel like it's been a while since I've seen you on stream. I hope you're doing okay, man. Okay. ifs.jl. So this will generate a Sierpinski triangle with a chaos game of n points. For a triangle with 3 points, let's say initial triangle with 3 points on the vertices of an equilateral triangle. A is 0, 0, B is 0.5, square root of 0.75, and C is 1.0. Okay, so this is the question, right? So this code is going to be the code that pretty much everyone in the algorithm archive uses to to create their own language implementations, right? So the question then is, should we hard encode the triangle, or should we allow them to take in triangle points? I feel like maybe we should allow them to take in triangle points, right? So let's see what happens if we let them read in triangle points. Something like this, which we'll set as a vector of tuples, I suppose is what we'll do here. But let's not specify the type right now, and we'll worry about that later. So what we do is we initially have some point, which is ran. It doesn't matter, it's just some sort of tuple. And then we say for I is equal to 1 to n, what we're going to do here is we're going to generate a huge number of points, okay? So what does that mean? Let's do, let's see. Oh, it ran. Where did I output it to? I output it to, let's see, Sierpinski square. Oh, did I just run Sierpinski? Probably. I didn't run Fractal Flame, did I? Right image pixel, Barnsley Fern. Yeah, here's our flame. Let's try that. Never mind, I screwed it up when I ran it. So let me see, I'm just going to run Control D. Mirage images. Nope. Control C. LS here. Let's do Mirage check. I don't know, .png. I don't know what I called it. Right. So what you can do is you can actually mess around by adding different iterative function systems together to create objects that are known as fractal flames. This is an entirely different algorithm with a lot of different steps, but it can create some really spectacular results. And again, Folster knows a lot about this. Now, Now, one thing I'm quite interested in about this, I would love to do these simulations again and get better visualizations, you know? But we're not there yet. So we'll do that again in a bit. Let's see. Hey, James. Yeah, it's been a while. I've been lurking for a while. Are you still living in Okinawa? No. So I moved from Okinawa to Boston, and now I'm in Alabama. So just because that's where I'm staying for COVID and everything. But yeah, so I actually work at MIT now. But I do genuinely miss Okinawa. Like, it's one of my favorite. It is by far my favorite. Like, of all the places I lived, Okinawa is my favorite. Genuinely love the place, and I really want to go back, you know? Bird Patrol Brasher, hey, how are you? I'm not sure if there are any that run these architectures, but it's part of just getting to know how certain things are implemented. Our professor is asking us to implement 64-bit specs on 370 while keeping it backwards compatible. I'm also going to write output file here. Why not? Cool. Just struggling through homework. I feel that. I feel like everyone's struggling through homework at some point in their life, right? So what are we going to do? We're just going to generate this point, and we're just going to say point location. So we're going to say out of I is going to be equal to point. Okay? And then what we're going to do is we're going to say, I guess it should be a tuple like this. Something like this should work. I don't know, just making things up. What language is this? This is Julia. It's one of it's a language I use very often. It's the primary language that I write algorithm archive chapters in, and also it's the primary language I use for work. It's relatively fast, within 2 times the performance of C. Really good with high performance computing. Great at accessing GPU memory. It's honestly, in my opinion, one of the best languages for scientific computing. However, it's new, so there's a lot of things that are kind of, you know, still people are still working out with it. Yeah, so if you haven't heard about it before, I mean, do you do a lot of Python? I do Python sometimes, but honestly, Julia has completely replaced Python for me. Tuple of array is not equal to array of tuples. You are correct. Yeah, you're correct. But it doesn't really matter. But I can do it that way then. Can I do 0 of tuple? Is this okay? Tuple of 2, maybe? We'll see. Well, actually, let's just run this in Julia and see what this does. I'm not really sure what it will do. I'm not even sure if this is appropriate syntax. So let's run Julia over here. And let's run zeros of, let's do 100. Obviously that works. So now we'll do zeros of tuple of 2. I don't know. 100. No, that doesn't work. Wrong syntax. Is there a way to do parentheses? No. Curly brackets? No, okay, I thought maybe. Type missing. Okay, so what if we do if are all, let's see, because that's my homework in right now. Yeah, Python's a very common language for homework. If or all. Okay, so I didn't necessarily, I mean, honestly, let's just do the following. Let's just do array. Let's just make it an array. And it will be 2n. Now it's 2n, is that? I think that should be right. So zeros, let's do zeros of 2n. Of 2n. Where n is 100. No, so we want to do n2. It doesn't really matter, but you know, why not? Okay, so we'll do n2 and we'll do out of I. Let's do out of I. So I is going to be n. So out of I, 1 is going to be point of 1. And we'll do point of 2. It's kind of messy. I mean, I could just do this. So we do rand, and then we just broadcast. Probably that'll work. Okay, that should do. There's 10 to 1. I think this is fine, what we have here. If that gets the idea across. I think this will work okay. So the point's just going to be like a random, it's just going to be a vector of 2 elements. And then we should be able to do that just fine. And I think that'll work. So now let's do, we'll have the output array here. And now we just have to move the points. The point is going to be equal to, I guess we'll just do, so we want to grab a random index inside of our triangle array. So we have triangle points. Can we just grab rand, what do we have? Rand n? What's rand n of, let's do 1 to 10. Does this do what I think it does? No, of course not. What I'm looking for is just, I want to grab a random index. What's rand n even do? Honestly, I don't even know. Okay, so let's try rand. So if I want an integer, how do I grab an integer, random integer? That's my question. So rand ABC. Oh, so it's rand within. So let's try a is going to be equal to 1 to 10. Let's do rand within a. No. Pick any random element from a tuple. Right. So I actually don't know what the colons do. Here, tuple of symbol. So if I do rand a. Okay, that is what I want. Perfect. So we'll do point is equal to, so we want rand of triangle points plus point over 2. So that's what we're looking for here. And I guess I should just do 0.5 times instead of that. Sure. Okay, so that's going to be our new point, and then we're outputting every time step, and the last thing we need to do is say, I guess, delimited right? What is it? So then we'll do DL, it's probably right DLM. Yeah, that's it. So we'll now do right DLM, and then we're going to output this to a broadcast. Yeah, so we aren't doing a broadcast here because we don't have a vector of points, right? So, I mean, we could just do, you're right, we could generate all the points at once, but I think this is also fine. So we'll do right DLM. We'll talk about that in just a second. So I think it's output file first, and then it should be the output. Yeah, actually, this is already messy because, like, we should be outputting line by line, I suppose. That's the question. Are we trying to minimize memory, or are we just going to let memory go by the wayside and we don't care about it, right? Anyway, this will work, what we have here. So let's just go ahead and run it and see what happens. And let's just, then we'll iterate on it in just a second. So we'll do Sierpinski chaos, and then we'll do, I guess we'll do 1,000, well, 10,000, why not? Triangle points, which are going to be, yeah, so I guess we'll just do, how do we want to do that? You're right, actually, I just realized, yeah, you're totally right. And this does have to be dot times. Oh, no, I think 0.5 should be fine, but the dot plus needs to be that. So then we'll do, the triangle points here are going to be what I have up there. So I think we can just do 0.0, 0.0. Then we'll do 0.5 here. And then the last one should be 1.0, 0.0. So that should work for triangle points. And then the last one we'll just say out. Out dot dat. Sure. Why not? I think I misspelled Sierpinski. So let's try running this once I fix that. Write this, go over here, include, and I guess IFS. Oh, where am I? Control D? PWD? What? Write this, write and quit, PWD. Oh, huh, okay. IFS, Julia, include, ifs.jl. Okay, weird, I couldn't find it earlier. Arrays could not be broadcasted to common size, got dimension with lengths 4 and 2. Where do we have 4? So let's check the line number. It should be 24. Oop. 17 maybe. Point is 0.5, so it should be rand of triangle points plus equals points. So rand of triangle points, why would it be 4? So then it says 24, but I know 24 is just down there. So point is 0 triangle points, and it should be broadcast onto point. So let's just see what happens if we create this tuple in the REPL really quick. And we're going to call this A is going to be equal to that. Oh, well, there we go. Right. Oh, I forgot a parentheses. Okay. So now let's do rand of A. This gives us 0. My bad. That's my bad. There's a dot here and a dot there. Okay, so let's try that again. Include. And see what we got. Okay, so it seemed to run. So now let's just run new plot. And then let's just plot out.dat. Yeah, let's just plot out.dat. Okay, so there's our Sierpinski triangle. Nice. Perfect. Exactly what I wanted. A nice equilateral Sierpinski triangle. Okay. So we have our iterative function system working, which is great. So now let's talk about what we want the code, how we want to write the code so it's clean. So this will generate a Sierpinski triangle with a chaos game of n points for an initial triangle with 3 points. There's a bunch of different ways we could write this. So let's go ahead and just, I'm going to do yank 6 yank here, and we're going to paste it down here, and we're going to modify the comment a bit in a second. So let's see, this will generate a Sierpinski for n points. Yep. So d $, given an initial triangle, initial set of 3 points. And in fact, we'll just say an initial set of points. Because actually this will, it doesn't have to be a Sierpinski. So actually this doesn't have to be a triangle the way we've set it up. This could be relatively straightforward. Let's just move down here. And let's, instead of calling this Sierpinski chaos, we just call this chaos game. Okay? Instead of triangle points, we call this shape points. Okay, and down here, we're going to say shape points. Okay? And now we're going to say for an initial set of points that span the shape we are, I don't know how to put this, the span, so this will generate a Sierpinski, well, this will generate, this function, this is a function to simulate a chaos game. I think that's all we need to say here. So the shape points, let's go ahead and put this here and say the output file is by default going to be out.dat, just so we have it there. So we initialize the output array and the initial points. We do point is equal to rand. Seems fine. Okay, so here's the question then. What we could do, so we could write this phenomenally easier. So what if we say point is going to be equal to the following. So let's comment all this out in here. And this could be some of the most straightforward code, you've ever seen, but at the cost of being very memory inefficient. So we'll say point is going to be equal to rand of 2n. Okay, I totally messed that up. It was 2n. And then we're just going to say out is going to be equal to, actually, out is going to be dot equals to, and we should just be able to do, oh, actually, we still need to iterate through, don't we? Yeah, no matter how we do this, we still have to iterate through. So I think we're going to have to, yeah, I think that's, oh no, we don't have to, we can map it. So we can map this on there if we wanted to. So we could do, let's see. Yeah, so we can map this on by doing like a map of something. No, I agree it doesn't make stuff better. But so in the Julia ecosystem, people tend to like this, and I tend to not like this. So I that's why I was talking about it. Look, I tend to not like this, but like the truth is that's what people tend to like in the Julia ecosystem, which is why I was trying to figure out whether we wanted to make it more Julia-esque. But yeah, Freeman, you seem to be agreeing with me that this is not the right way to go. And I agree. I personally don't like it when people do that. But again, it's what people tend to like in Julia. So, in which case, I'm kind of happy with this implementation. I mean, maybe we turn this into a tuple instead of a here. And this should still run just fine. Control D. So we'll do include IFS, still runs just fine. Can you plot it with 0, 0? Yeah, we can do that plot really quick. Let me just, yep, so let me see. So we'll have Sierpinski Chaos, and I'm just going to comment that out from now, yank and paste. And this is no longer going to be called Sierpinski Chaos, because now it's called Chaos Game. And this will also be called Chaos Game. Okay, and it's a simple Chaos Game, so we don't have to go crazy with it. And let's just say shape points are going to be equal to whatever Folster just gave me. So let's do this. So that's 0.1. And then I'm just going to move on to the next line just so it's a bit easier for me to see. This should be... one second, I missed a... this and that, I believe. So the next will be this guy. Okay, so I think that's that. I think that's your initial set of points, right? So you said you wanted to do it with this. So let's see what happens if we read that in. So we'll do shape points here. Okay, and let's see what that does. So we'll do include ifs.jl, no method matching chaos game, int64, n tuple of 4. Huh. Oh, Freeman did that. I'm so sorry. For some reason I read that as Folster. My bad. I totally just misread that. So no method mentioned chaos game int64 n tuple 4 tuple float 64 string. What? Oh, that's because I changed it, so it's now output file. So let's just dt here. And let's do the same over here. Okay, so we'll include IFS. No method matching float 64. Okay. Wait, why is this a float 64? What? No method matching float 64 and tuple float 64. Any operators. What? I don't understand why. Let me control D out of here. Julia, include IFS. Okay, I thought maybe that would solve it, but it doesn't seem to be solving it. Shape points is equal to this. So 0, 0. Oh, let me move that down to the next line as well. Okay. Yeah, let's see. Int shape points. I don't think anything's different. What happens if I run this chaos game? Yeah, that also screws up. Crap. No method matching float 64. Why is it considered to be a float 64? It's not a float 64. It's an int. How though? No method matching float 64 and tuple float 64. What? What? Am I calling it at some other point on accident? Chaos game. Here. Nope. Is it even on this line? Okay. Both are tuples before one. Oh, okay, maybe. Yeah, okay, let me see. Out is 0. So yeah, maybe this has to be an array. Let's go this. Let's do include IFS. Yeah, okay. If that's all it was, that's fine. Let's go here. Let's run GNU plot. What? Okay, GNU plot. And let's go ahead and plot out.dat. Okay, well that didn't do quite what I was expecting because I forgot that this was commented back in. Okay, Control D. Include IFS. New plot. Plot. Right, it's just a random parallelogram. Right. Both are tuples in the function definition. You change rand and rand to be tuple. Yeah, I thought it would be fine as a tuple. I don't understand why it wouldn't be, but that's okay. It doesn't really matter, and it's fine. Now the second one, yep. I can do the second one as well. So 0, 0, 0.5, square root of 0.75, 1.0. Did you just flip this guy? Well, yeah, this should be the same thing. Okay, Control D. Include IFS. GNU plot, plot. Yeah, it's the same thing. Float tuple is not defined, while 0.5 times an array is. Okay, fair enough. Thanks, Freeman. I appreciate that. But yeah, so you're actually running into the same situation that we said before, that when you do an iterative function system, or rather a chaos game on a square, you just get a square of random points, which is not quite what you're typically looking for with this type of stuff. But that's the entire next chapter on restricted chaos games, which is something we definitely will cover. But for the first iteration, I just want to talk about iterative function systems and go from there. So let me define shape points here. Something like that. And go here, and we're going to do Control D, include, new plot, plot. So there's our Sierpinski triangle that we had before. I actually kind of like this run better. But also, what I don't like about this is that we're using a tuple when I feel like this should be an array. Can you get a cool star from 5 points? Wait, what do you mean, cool star from 5 points? Oh, we can try that. Yeah, why not? I'm actually not sure what happens when we try 5 points. So let's go ahead and comment this out. Well, let's do yank for yank. Paste it up here. And we'll comment all of this out for now. And then we'll fix it up after that. So what 5 points are we looking for then? Let's just do 0.5 square root of 5. So let's do yank paste and yank paste. So we're going to do 0.25. And we're going to do 0.75. And let's just do 0.5. Put a 0 here for consistency. Okay, so here are our shape points. Let's Control D, include IFS, extra token. Yes, that's because down here I think I have an extra token. How did that happen? I have an extra token there, extra token there. Okay, so now we're going to run in GNU plot, plot out.dat. Let's move these guys in a bit. So it's going to be at 0.6, and this one will be at 0.4. Include new plot plot. There's something going on here, but I'm not sure. Hey, Perps, we're using your color for new plot. I hope you don't mind. Let's see. Cool. Thanks guys so much for all the chat, by the way. Really appreciate it. But there is something. There is something here. I know there's something here because I've seen it before, and I think it's even on Wikipedia. Chaos game. So let's go to Chaos game here. And I feel like if you just scroll down here, yeah, this plot I think is what I was looking for. So a point inside a pentagon repeatedly jumps. Okay, so I think this is actually an entirely new chapter for restricted chaos games. There's a lot of really cool stuff we can do with this, but I feel like, you know, we first do iterative function systems, and then we do restricted chaos games. I've got I sometimes accidentally jump too far ahead. So like I like every one of my videos and chapters to be like really short and concise, so that we can get more content out. And so I think that's what we'll do. Let's go ahead and close this up, and let's just move back, remove these shape points in here. Okay, I think this is relatively, I mean, it's okay. The thing I don't like is that I think I want to define this as an array. So we'll do 0, 0. I think this is the syntax for an array. But I don't really remember. So I think this is it. It used to be this. It might not be this anymore. Point n. I'll try that in just a second. Let me just make sure this works. GNU plot. Oh. Include. Yep. GNU plot. Plot. It didn't work. Did not work. Did not work at all. And it didn't work because if you do rand of shape points, yeah. Okay, that's obviously not going to work. So we'll do, I guess it has to be an array on the inside. That's the only way to do it. Darn, that's super ugly. But it is what it is. It's fine. Oh well, it is what it is. Control D. Include new plot. Plot. Okay, so let's try what everyone else said now. So we're going to comment this out, and we'll try the suggestions by Freeman, and I believe also Foldster. So let's go here. And so you say point n is going to be sign. Oh yeah, so we have to modify the point. When is your maximum number of points minus 1? Okay, so let's try that. So point n. Wait, no, I don't know what you're trying to say there. Let's do Freeman's points here, and then we'll come back. So let's just grab these guys, and we'll say shape points is going to be equal to, and we'll just put an underscore there. Write that. Go over here. Control D. Control D. Include. Then run new plot really quick. Plot. That's better. But it's still not obvious, right? What happens if we increase the number of points by a factor of 10? Control D, include new plot. Yeah, that, I mean, maybe it's what we're looking for, but it's not clear with this visualization. So let's do point type 3. Yeah, that didn't help at all. Point type 7. So now they're dots, but that also didn't help in any way. It might be actually what we're looking for, but it's hard to see because it's all chaosy. Cool. So let's go ahead and close this. So the points are being plotted too big. If you want radially distributed attractors. So what if we do point size 1, 0.5, 0.1. 0.01, 0.05, and let's just make that big. Ooh, that's really hard to see on my end, but maybe it looks okay on stream. Yeah, maybe not. Let's make that a bit smaller. Move it up here. Move that in here. Ooh, new plot. Hello. Let's see what you do, my friend. I've seen this error before. The way it's generated is broadcast X. This is generated. Oh, right. You just rotated it. Let's see. Points are being plotted too big. If you want radially distributed attractors. So my question to you, Foldster, was when you said point n is going to be equal to sine of pi times n over n. Yeah, I'm not sure exactly what you were going for there. Sorry about that. But I think this is actually where we'll end stream for today. Let's go ahead and clean up the code a bit. I realize, yeah, we didn't get as much done, but also it's a short stream, so I think that's okay. DD there, remove these guys in here. I I'm just defining the attractor points location. I'm defining the attractor point locations for any n. Okay. Sine of pi to n. Let's see. Houdins, thanks so much for following. Street Maniac, thanks for following. Really appreciate it. Cool. So this is good for this. I'll come back and we'll look at the code again tomorrow. Yeah, we'll look at the code again tomorrow. So let's go ahead and do git add ifs.jl, git commit -m, adding first iteration of ifs code with Julia. N steps rotated. Let's see. So where n is the number of attractors minus 1. Oh, I see. I see what you're saying. N steps rotated, irrelevant for this attractor. N to gone. Okay, I think I understand. So I think that's it for today. Let's see who's live and who we want to raid at the end of stream. We've got Kitboga, Bernie Sanders, Dowright, Das Valdez, Fractured Chemist, Microscopy of a Swamp. I feel like we haven't raided Freck Chemist in a while. She came by our stream the other day. I feel like maybe we should do that. So she's a cool chemist. She talks a lot about, you know, science and stuff, but also about a bunch of other stuff. So I think she's really cool. Let's go and raid her. She sometimes stops by. I think it's worth. I think we should definitely support her, you know? You're banned in her stream. Why are you banned in her stream? Fixing the Zika, thank you so much for following. Really appreciate it. Oh, okay. Well then, if you're banned in her stream, I guess we'll go to someone else then. How about, let's see, what's CM Griffing doing? Hackathon Showcase bot. That sounds interesting. Let's raid Bernie Sanders. We could do Kitboga. I mean, like, I never raid Kitboga because he's so big, but also, I'm a big fan of Kitboga. Like, I really like his stuff. So I feel like some people in the channel will probably just go to his channel anyway once I'm done. What do you guys reckon? We could do Kit. Yeah, maybe we do Kit. Why not? Sounds fun. Let's do it. Let's do it. Why not? He's a good guy. I really like his channel. So for those of you guys who don't know, Kitboga, he's a great streamer on Twitch. He makes a fake bank just to trick scammers. He calls scammers, and he has a whole bunch of different voices that are really funny. He's just a good guy. I like his stuff. I think everyone knows Kitboga. Yeah, okay, maybe everyone does, but I'm a big fan. Let's just go ahead and raid him today. I mean, right, I could raid someone else, and probably it would matter more if I raided someone else. What do you guys think? Right, so Kitboga, basically, he calls scammers, and he gets the scammers to, like, he knows the entire scam, so he just kind of goes through and just pretends to be this character that doesn't understand what's happening. It's just good, wholesome fun. Let's raid him. Let's go. So we'll raid Kitboga at the end of stream. Let's go ahead and do that. And, yeah. Anyway, guys, thanks so much for coming in. Have a great day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos, where we do maybe not as much Julia, but we do get more algorithm archive work done. Pretty happy about that. So tomorrow we should be finishing the chapter on iterated function systems, and we should be hopefully getting a video out this weekend. Yeah, we're making progress. Thanks, guys, again for coming in, and I'll see you next time. Bye, guys.